previous job I worked on. Before that, I was working elsewhere as a lecturer, and then I also went to Japan.
Okay.
This place is probably the longest.
I like the city.
Yeah, the
I was there yesterday, and it was
yeah, nice.
like it's not big, but it's also nice.
It's quite comfortable. I think it's better I like it. But I do also.
I guess cold is good.
Give me the mic. Is it okay? Okay, welcome back. I hope you enjoyed the tea. So, it's my honor to introduce you the next speaker, who is Abhinav Gupta, and he's an associate professor at the Robotic Institute at CMU. He's also a research manager at Facebook AI Research. His research focuses on scaling up learning by building self-supervised, lifelong, and interactive learning systems. He's a recipient of several awards, and actually it's a rather long list, including the ONL Young Investigator Award, the Palmy Young Research Awards, the Sloan Research Fellowship, the Akata Foundation Grant, both Young Faculty Fellowship, YPO Fellowship, and a number of Best Paper Awards. So his research has also been featured in Newsweek, BBC, Wall Street Journals, Wired, and Slashdot. So today he's going to talk with us a bit about supervising and empowering visual learning. So without further ado, I will introduce him here. Thank you very much.
Thank you. Okay, since all of you are here, I'm going to assume that you all know what has been happening in our field. Our field has been going through some kind of a revolution. And this is mostly because of the significant advances in the field of visual representation learning. And that is, of course, thanks to the deep network, deep learning, convolutional neural networks. People can call it by different names. But if you think, while we have made these advances, most of the learning is still very narrow in scope. So if you think of how the learning works, what you do is you download lots and lots of images, sometimes millions, sometimes hundreds of millions, whatever you like. Then you try to label them efficiently, something what Vito talked about. Or you say, okay, maybe I can label it weakly or something. And then you learn your model. Now this kind of learning is supervised and passive. There are two words here. Supervised, because you gave the supervision. You said this is a car, this is a cat, and so on. Passive, because the model had no choice. You sent the batch of 256 images, and it has to learn from those 256 images. Now, compare this kind of learning to how learning happens in humans and animals. First, learning is quite unsupervised or self-supervised in nature. No one is giving you 100 different kinds of mushrooms or 200 different kinds of dogs, which is what is there in ImageNet. And until you know all these 200 different kinds of dogs, you cannot learn the visual representation. Similarly, learning in humans is continuous and lifelong, unlike what we do in our current models. And so we continue to learn every day. Even now, today, we learn new things every day. And in this continuous lifelong learning system, we are reusing our knowledge, and we are building upon the existing knowledge. The third most important thing about human learning is that it is interactive in nature. You are not waiting for data points to come to you. You create your own data points. That is very, very crucial. Finally, learning in humans is integrative. That is, you are learning from diverse sources for diverse tasks. You are using audio, you are using vision, you are using text, whatever comes to you. You use all those sources and you learn one common model for different tasks. But forget all these reasons. They don't matter. There is one bigger reason why I think the current paradigm of learning is just not useful. And that is, the manual labeling is just not scalable. And so, for example, ImageNet, which was one of the biggest data sets before Vito's open images and so on in detection, it had 1 billion bounding boxes, which took almost 4 to 5 years to collect. Now compare this to how much data we humans generate. For example, Facebook, and this is an older number, has more than 600 million images uploaded daily. And then there are these domains where manual labeling does not even make sense. For example, actions. Most of the current approaches use lab setting and learn from 1,000 examples in robotics. And now, if you compare this to how humans In case of humans, we are doing thousands of interactions every day. And so consider how much data we are learning from when we are trying to do actions. So my research focuses on scaling up learning and empowering visual learning by building self-supervised interactive physical agents. And I'm going to come and explain each of these terms slowly. But first, let me explain what do I mean by visual learning, because this is the basic thing which I'm trying to do here. So for me, visual learning consists of two parts. The first part is the representation learning. And this is the learning where you are learning your features. Whatever you use from your ImageNet network. That ImageNet is used to train an initial network before you fine-tune. That is representation learning I'm going to consider. And then there's a task-specific learning. And this is where you fine-tune for a specific task, like for detection or whatever you like. And so visual learning composes of both representation learning and task-specific knowledge. And so what I want to do is, I want to improve both these things, and I want to learn both the representation and the task by using these self-supervised, interactive, and physical agents. So there are these three different parts. The first part is a self-supervised. So what I'm going to talk about in the first part of the talk is how you can scale up learning. Go from million images that we currently use to hundreds of millions of images by using self-supervision. In self-supervision, you are just going to use the data itself to provide supervision. There are going to be new different kinds of tasks, and those are going to help you learn the representation itself. And so this part will focus on the representation learning. In the next part, I'm going to move on to the task-specific learning. Now, when it comes to task-specific, again, the paradigm is something like this. There is a model, and then someone is feeding it supervision, like 250. So you can think of this spoon as 256 batches of images, like a batch size of 256 is being fed every time. And I believe that this is a completely wrong paradigm to learn. What we need is interaction. We need these models to select their own data, that I want to learn about this next. I want to learn about this next, and so on. And so I'm going to argue that interaction is going to be crucial. So first, I'm going to talk about how we can build interactive agents which can decide what information do they want to get from the environment itself. And hopefully, if they are going to decide their own data points, they are going to be more sample efficient. I'm going to evaluate it in the context of the VQA problems. But this kind of interaction, where an agent is asking questions about the world, is still very limited in nature. Like when do babies start to ask questions? Maybe 2 years, 2.5 years, and so on. But most of our interaction as babies is something like this. We push objects, we poke objects, we throw objects around, we put objects in our mouth, and this is the kind of interaction. And each of these interactions is a data point. The baby is trying to see how the object behaves when you throw it, and so on. And so to do such kind of physical interaction with the world, one idea is to use robots. We want to use robots to learn about the visual world itself. Of course, the big problem that is in front of us is that robotics is probably a brittle field than what vision is. I mean, vision has made super advances, but robotics, I'm not sure. Can I use robots to collect millions of data points, billions of data points, and so on? And so the last part of the talk, I'm going to talk about if we have to move towards this physical interaction, what do we need to do? I'm going to give you some examples that we have been doing in robotics and how we are going to move forward and so on. So this talk has three different parts, and I'm going to go through one by one through each of them. So let me start with the first part. I'm going to try to learn visual representation using self-supervision. Now, before I go here, I think the first question anyone needs to ask me, see, we have this 1 million ImageNet dataset, or now there is, let's say, 10 million newer dataset. Do we even need those billion images you're talking about? What if there's a hypothesis that we don't need anything bigger than ImageNet? ImageNet is just good enough to learn the best visual representation that is out there. So that's the first question we need to ask. And in fact, if you think what we all have been doing, I don't know, knowingly or unknowingly, our research trend is suggesting something. So for example, since the 2012, when this deep learning revolution came, the GPU powers have been increasing. NVIDIA is really good at it. They have been every year, they will come out with a GPU that is 2x faster or maybe 10x faster and so on. So the GPUs have been increasing. Our models, we researchers have been doing good as well. We have been increasing model sizes dramatically as well. But until 1 year ago and so on, the data set size remained constant. Everyone was using an ImageNet pre-trained network, right? I mean, that's how you start. When you are trying to train for your task, you will start with an ImageNet pre-trained network. what is special about ImageNet, like 1 million images? Why not collect data set as well? Maybe if we have collected data set, we would have had 100 million, 200 million images by now. So in the first part, I want to explore, okay, what if we have tried to scale up the data set size? And so while I was at Google, I worked with Chen Sun, Abhinav Srivastav, and Saurabh Singh, and we basically tried to use the 300 million images, that is an internal Google data set, which is noisily labeled, and we wanted to see, if we train our network using this, how good of a visual representation can we learn? We want to see, like, does the performance increase with data set size, or maybe it becomes stagnant at ImageNet performance and it will never increase. If that is the case, all unsupervised learning, not useful, right? I mean, because nothing will help more. Even if more data is not helping, what's the point of unsupervised learning? So there are two findings. I'm not going to go into detail. This is just like plain vanilla training, just a bigger data set and training and testing it out on different tasks. And so the first thing we found is that by using 300 million images for training visual representation, performance improves on every task. This one is obvious, right? I mean, COCO improves by 3%, VOC improves by 5%, segmentation 3%, and so on. But I think the more surprising finding is that the relationship between the amount of data and performance is log linear, and it continues to be there even at millions of images. So for example, even at 300 million images, this does not seem to be saturation in the log linear graph at all. And so that tells us that more and more data should be useful. I mean, our performances keep on increasing even at 300 million scale as well. And interestingly, in a recent study, Facebook, and I think this is an ECCV paper, they trained another data set with 3.5 billion images, and it even tends to continue there. The performance keeps improving as you keep on feeding more and more data. So this is really exciting, right? More data means more performance. The only problem is labeling of data. How do I label it? And so that's where this first part of the talk comes in. Like, can we somehow get rid of this idea that we have to label data to learn representations? So before we go here, let's try to take a step back. Let's try to see what does ImageNet do. So our goal when we are trying to learn features is that we want to learn some kind of invariances, right? Illumination invariance and so on. The hardest of the two invariances are instance invariance, that is two cats, cat A and cat B are still the same category. So that's called, I'm going to call it instance invariance. Different cats are still, we still want them to label cats. The second one, we want to call it as viewpoint or deformation invariance. This is a clicker, this is a clicker, this is a clicker, and so on. Like with different viewpoints, we still want to call it a clicker. And that's what we want our features to learn, both instance invariance and viewpoint invariance. In self-supervised learning, what we try to do is, we try to come up with some novel tasks which are where ground truth is going to be free, like no human has to label ground truth. And yet, it will help us learn invariance. Seems like a magic, but it's possible. Let's start with a very simple example. All of you, this is a black and white image. What color is this object? Hopefully all of you can solve this problem. And hopefully all of you are thinking that this is skin color, or whatever you want to call it. And so this is what you have been thinking the color looks like. Now, of course, the question is, how did you solve it? Right? So what probably you did was, you said, oh, this is a hand. I know hands are made of skin, so this might be something like that, skin color and beige and so on. And so basically, what you are using is semantic information. So to solve this task, you need semantic information that this is hand. And so we can use this kind of a knowledge to train our visual features. So we can have a network which, given a black and white image, tries to colorize the image, and we are assuming that to solve this task, the network will need the semantic information. It needs to learn the semantic information to solve this task. Ground truth is free, because you can take colored image, convert it into black and white, and then feed the network to say, can you color it now? So every image, you have the ground truth, which is the colored version of it. And you are getting free ground truth and so on. And so there have been a range of self-supervised system in the last couple of years. There have been like hundreds of papers that are coming in which are trying to use this self-supervised learning. For images, like for videos, like coming up with different tasks for each of these categories. Now in this talk, I want to talk about a couple, which are of course my own work. And so the first one is the relative spatial location task. So in this task, what we are trying to do is we take an image, we pick out two patches, and we ask a network to predict the relative spatial layout of these patches here. So these are the two patches. The network has to predict what is the relative spatial layout. Now again, to solve this task, you need to understand that this is a cat face and this is a cat ear. And so once you have this idea that you know that once the face is here, the ear will be somewhere here because it's a right ear. You can even know by the shape that this is a right ear. Now again in this case, to solve this task, you need semantics. You need to understand that this is a cat and so on. And the ground truth is free because here is an image. I just took out 2 patches from this image. And so I really know what the answer was to this thing. So I can have billions of images, take out billions of pairs of these patches, and train my network to solve this task. And with this, I can learn a visual representation. How will I check if I learned a good representation? I'm going to take this network and fine-tune it with a VOC, like only 5,000 images. So hopefully the network has done most of its learning when it was doing this, and it's just using this, learning the mapping between the features and the VOC categories. So if you do not use any pre-training, you get 39.7 mean average precision. If you use ImageNet to pre-train, you get 70.9. And now if you're using something like relative spatial layout, you get 62.6. So this is good. I mean, it gets us somewhere without any ImageNet labels, like 1 million ImageNet labels. Let's try to understand what this network was doing. So this network is basically trying to learn. It's very good at instance invariance because 2 different cats will have still same layout of face and ears. So it will be very easy to learn for this. It uses the context to learn that these 2 are same categories because the spatial arrangement between the face and the ear remains the same across these 2 examples. What this approach is really bad at is the deformation invariance because now the relationship between the face and the ear changes completely. And so it does not know that this cat and this cat are also similar because the relationships are completely different here. And so that is why this approach is good at instance invariance, but really bad at learning viewpoint invariances. And so what is viewpoint invariance? Coming back, I want to learn that this is a pointer, this is a pointer, this is a pointer, and so on. How do we learn something like this? Again, in a self-supervised manner. I don't want to label images. That's my first goal. So, well, there's a simple answer. I automatically created this data set when I was doing this for you. Videos. And so what we can do is we can start tracking objects in videos. So for example, we can start tracking these bikes and so on. And hopefully, if we are tracking objects, we will see them in a different viewpoint. So you see a person first in the standing, and then by the time the video finishes, he's on like a lying down position and so on. And so it's a deformation that you can learn. So this is the simple idea that we do. We basically take videos, we start tracking patches, and then we learn a simple network, which takes the first patch of the track, the last patch of the track, and a third random patch. And it tries to learn an embedding, which will put this patch and this patch very close to each other in the embedded space, the FC7 space. And the third patch will be as far away as possible from these 2 patches. So this simple idea that we are trying to just take the patches in the same track close to each other. And so this approach is going to be really good at learning viewpoint and deformation invariance. And again, if you test it, it turns out that it performs reasonably well. It does 62.2 on the mean average precision. So this is good. So we have 2 approaches. They both seem to learn complementary things, and they are both coming close to each other, but still very lower than ImageNet. So the next obvious idea is somehow combine these 2, right? I mean, they are learning, one is learning instance, other is learning viewpoint, combine them. So the idea again we used is very, very simple. We are going to take hundreds and thousands of videos, download it from YouTube. We are going to use the first approach, which was learning the instance invariance, to figure out what patches look similar across 2 different videos. So here is a patch A and patch B. It looks similar across 2 different videos using the features learned from the first approach. Now we take patch A, we start tracking it in the video. We take patch B, we start tracking in its video, and here is what we get. This becomes something like this. This patch becomes something like this. So until now, we have been training networks which will say A and A prime are similar, or A and B are similar. So what we can do is you can say train a network which will take all the 3 as similar, but you can even do better. You can use transitivity. You can say if A is similar to B is similar to B prime, then A and B prime should also be similar. Similarly, if A is similar to B, A is similar to A, so B is similar to A is similar to A prime, then A prime and B should also be similar. And so you can augment your data by doubling these extra edges, the transitivity in the similarity space. And so what you get is like more examples here. So here's an example that we started with these two as similar bikes, and then we added all these four, and we said all these four should be similar. So the idea is we are making the circle of our confidence bigger and bigger, slowly and slowly. We are not taking a huge jump. And so now you use this simple approach, the embedding approach, where you try to learn that all these four patches should be as close to each other as possible. And by doing this, something as simple as this, you see that our performance jumps from 62 to 65, and it's still very far from ImageNet. It's still 5% away from, 6% away from ImageNet. If you do it on Coco, it actually is even closer. So our approach does 23.5, and Coco, like ImageNet pre-trained, does 24.4. So we are less than 1% away without using any ImageNet labels at all in learning the features. And so this is basically promising, but of course there's still a long way to go. This 0.9, this might be a little deceiving, by the way, because Coco by itself is a big data set, and that's why a lot of feature learning might be happening when you're fine-tuning for Coco. I think this is a much better one. There's still a long way to go, 6%, but there is still a hope that we can somehow maybe increase data set size. So because, for example, this one was being trained with 100,000 videos, so we can use more, maybe like million or billions of videos, and hopefully the performance can scale. Okay, so this was the first part where we are trying to basically go from 1 million images to maybe hundreds of millions of images. And the biggest bottleneck remains to be labels, so we are trying to get rid of the labels. Now let's move to the second part, which is task-specific learning. Now we are trying to map features to a category, let's say giraffe, deer, and so on. And the standard way that we have been doing this is something like this. And I keep coming back to this image. There is a model. We decide randomly 256 images with their labels, and we feed it to the model. It uses it to compute backprop, and so on. The model has no choice. It has to see those 256 images and nothing else. And the problem is that sometimes it can be crucial that maybe we are wasting our batches. Like we have already learned about cats, and you're still feeding cat images to your model. That seems to be waste of resources and so on. So the question is, how much supervision is good supervision? Of what kind of categories do you want to learn and so on? So one solution is to not stay in this world of passive learning, like batches and like offline learning essentially. And the better idea would be to move towards interactive agents. So these agents are going to themselves decide what information they want and how they are going to get it. So our hope is that they are going to be, by doing this, they are going to be sample efficient. With less than half the data, they can get the same performance. Now what we are going to do is, we are going to build these interactive agents in the context of VQA task. In a VQA task, we'll have an image that will be provided to the agent. The agent is going to decide, rather than like pre-supplied question, it's going to decide what question it wants to ask about this image. And so it asks the question, then there is an oracle, that can be human labeler. And so the human labeler decides, oh, for this question, this is the answer. And it basically provides the answer. And so the agent is itself deciding that maybe right now it wants to ask about the girl, or maybe it wants to ask about the bed, or maybe it should ask about the paintings, depending on where it is in its stage of learning. It will decide what question to ask at what point of time. And so we are basically acquiring supervision by interacting, by deciding ourselves what question we want to ask, and so on. So just to make sure how it is different. In VQA, you are given image, question, and answer, a tuple like that. Here you are only given an image. And now given an image, you decide yourself what the question is, and the answer is provided by the oracle. This is like standard active learning kind of a setting, but in VQA formulation. Now the good part is that we can really evaluate this easily, because this is standard VQA task. So we are going to have these held out questions, and we are going to basically see the performance. Like, can our approach get the same performance on VQA by just half the questions rather than the amount of questions asked here? Now for the development, for the first part, I'm going to be using the Clever universe. So this Clever is a synthetic image data set. Basically, it has 70,000 images, already has 700,000 image question answer tuples. And this is what the images look like. And here are some of the example questions that exist here. Now, why are we using Clever at the first shot? Because Clever has this thing that you really do not need Oracle to answer the questions. So all the questions can be converted into a program. And because it's a synthetically generated image, you can use the program and the synthetic generation, and you can basically automatically give the answer here. And so basically we can do a lot of iterations, development iterations on this data set essentially. Now even though this is Clever, this is still a very hard problem. I want to point that out. especially because the first challenge that we need to solve is that we need to make sure that we are generating valid questions, not random questions. And they can be like really invalid questions. For example, in this case, there's a question, what is the color of the ball? This is an ambiguous question. It could be this ball or this ball or this ball. So there is really no way to answer this question. You can be mentioning an object that is not even present. What is the shape of the purple object? Where is the purple object in this image? So if I put some question like this, the oracle is going to get confused, or if it was a human, he's going to get confused. So these kind of questions are not allowed. I'm going to waste my data points here if I do that. And here's another example. I'm basically talking about an object with wrong relationships. And again, something which I should not be doing. So this is the first problem that I have. I need to make sure that I generate valid questions. The second challenge is, remember, this agent has to decide what question it wants to ask. So it somehow has to have this introspection module or some kind of self-evaluation module. It needs to somehow know what it knows and then decide what next thing it wants to get. And this modeling of what the agent knows is a really tricky problem. I mean, we have had a lot of problems with this approach, especially in the deep learning scenario. Like whenever your deep learner produces an answer, it's 100%, like 90% confident that it is the right answer. So it's really hard to use standard approaches like entropy and so on to basically decide what the model doesn't know and what the model knows. So our approach is actually very, very simple. So given an image, the first we generate a question proposal module. This question proposal module generates hundreds of these questions, which are possible questions to be asked in this case. Then we have a standard VQA module. This is the question answering module. For each of these questions, this question answering module creates a set of answers. That, okay, maybe for this question, this is the answer. For this question, this is the answer, and so on. Now, using the answers that the VQA produces and the question proposals, there is a selection module that is going to decide which of these 100 questions it wants to ask, depending on what answers the current module is generating. Now, it basically selects the question. It sends the question to the oracle. Oracle sends back the answer. Now, the oracle can either give the answer. It can also say that the question is invalid. There's no answer here. And that is for the cases which I just showed, essentially. Now, like all standard approaches for our active learning, we are going to assume that there are a few IQA tuples that are given to us. So in this case, we are going to use 10% of the IQA. Like out of 700,000 questions, we are going to use 70,000 to initialize our question proposal module, question answering module, and so on. And from there on, we are going to start to improve the performance. So let's look at the question proposal module. So a question proposal module, I mean, all these modules are very, very simple. Given an image, you first generate their features. These features go into an LSTM, and that generates a question. You can also condition it on the question type. Like, do you want to ask color-based question? Do you want to ask numbering-based questions, and so on? And so that tends to generate much more diverse questions. So we are going to use this, condition it on the question type. Once the question is generated, we are going to have a validation module, which is going to basically evaluate, is this question valid or not? And again, this module is learned from the initial 70,000 images. Now, it is interesting that this is a very important module because initially, probably we are going to generate a lot of questions that are invalid. But by the time we are at this 150,000 iterations, we'll be basically generating only 10% invalid questions of 5, and as we move forward, 5% invalid questions. The second part of the module is the question answering module. This is a standard VQA. Choose what you want. In our paper, we have 2 or 3 different modules that we use. Here I'm showing the simplest because it's easiest to explain. Give a question, image features, use RNN to encode the language, and provide somehow magically the answer. And so this is a VQA module. No research here. We just use off-the-shelf stuff. The last question, which is the most interesting thing, is how do you decide what proposal, what is an informative question, which one should I ask? Now, this informativeness, we are going to use 2 terms to define informativeness. The first is, what is the probability of each individual answer given the image and question? So for each question pair, you can say, okay, this question, the answer is likely to be red. For this question, the answer is more likely to be yellow, and so on. So you're modeling this probability of answer given the image and the question. The second thing that we use for deciding informativeness is the derivative of accuracy. So for each answer, we are going to say, okay, how much the model is improving over iterations. So for yellow, the model seems to be improving a lot, but for red, the model is plateaued already. So basically, we are seeing how, for particular answer, the model is improving. So it's a very different way we are modeling it. For each answer, there's a different derivative. So we are doing class-based accuracy measuring. And so our informativeness is something very, very simple. It's the probability of the answer, and then how much improvement you are getting in performance for that answer essentially. So this is another way to look at it, is that this is an expected gain in accuracy. So the probability that this is going to be, our answer is going to be red is 0.9, and for the red answer questions, I am improving performance by 0.1. So the overall improvement I expect to gain here is 0.09 essentially. So you want to select things which are where you are confident about red, and the classes for which you are getting the maximum performance improvements currently essentially. So the way to look at it is, if you're asking questions where the answer is yellow, keep asking yellow questions until you have learned what the yellow is essentially. There's another way to look at it, just to explain it more. Let's look at when HQ, this informativeness, is going to be low. There are two cases when it's going to be low. First, when this probability term is low, which is when you're confused essentially. So in this case, we are assuming question is difficult. And when the question is difficult, you will not have a very specific answer, so it will be very high entropy and you will have very lower term here. The second case is that it will be low when you're saturated the accuracy. Things are not improving anymore for this answer. Like for yellow, you're not improving anything anymore. So you have stopped improving on that concept. And so basically what we are saying is, stop asking questions which are too hard. You only have to ask the right questions at the right time. And similarly, focus on concepts where you're improving. So if you are doing 50% on yellow, keep asking yellow questions, because by asking a few more yellow questions, maybe you'll understand what yellow is essentially. And so that's what the insight is. Just to point out, we also try RL, like agent, something like what Vito was saying. In our case, RL didn't work. So this, again, hand designed model seems to be working really, really good. And it has a lot of background in the literature. So there is a lot of literature which supports this approach essentially. And so our final model looks like something like this. You have basically image, you generate question proposals, you use the VQA to figure out the probabilities, and then decide what question you want to ask. And if the oracle gives them real answer, you retrain your, use this to fine tune your model. If the oracle says that the question is invalid, you improve your question relevance module. And so here is what the performance looks like. So on the dotted line is the standard VQA if you are just adding randomly images. On the solid line is what if you're using our approach to add questions. And you can see that at some point of time, we are 40% more sample efficient. And at this point of time, we are starting to run out of questions here. We are already reaching almost the top of the performance. And so at this point of time, you really want to go out of the clever world and ask questions essentially here. Interesting thing is, what kind of questions does it ask? The whole thing that you want to ask questions one by one of each type. So initially it asks, like in the first few iterations, it was asking like questions about colors, then about shape, then it asks questions about the counting, especially but not explicit questions, and then finally it asks explicit questions about counting, like how many large metal spheres are there and so on. We can also compare to standard ways of active learning. So for example, you can choose random, you can choose max entropy to select the question, you can use maximum variation ratio, and then ours is the top. And you can see our approach of interaction seems to be the best. But of course, this is just VQA. So we want to see if this will also transfer to the real world images. So then we use the VQA of one data set, and we are basically, the only thing we are going to do is we need to somehow have Oracle. We cannot have humans in the Oracle because it's going to be too expensive. So what we did was, we defined Oracle as, if there was a question in the training set, you give the answer. If there's no question, such question. So if you ask a question about a girl and there was no such question in your training data set, you say that this question is invalid. So it's a very bad Oracle, you have to assume here. And even in this case of bad Oracle, our approach seems to do really good compared to random, for example. So our approach gets 46.1, whereas random is only at 38.7. And so it seems that our approach of generating questions seems to be really, really good here, essentially. Okay, so this was the second part of the talk, where we are basically going from passive learning to more interactive learning. But of course, I made a big deal initially that we have to be physical. Physicality is the first couple of years of learning in babies, so physicality is important. And the question that I was trying to ask here is, can robotics really scale? Can we collect thousands of examples using robotics? Or robotics just probably can only work with few hundred examples? So as a first step, so we have been taking a step-by-step approach. As a first step, what we tried was simple grasping. So in our system, what we have is a robot. It goes and tries to grasp objects randomly on the table. So it picks a random XY location, goes and tries to grasp it. Now, because it's random, it can be sometimes successful, sometimes it can fail. And the success is measured by the force sensor in the wrist. So whenever it will be successful, the face will turn happy. So like it's successful and the face turns happy here. So it's automatically measuring the failure and success. No human label is required here. Now, you do this not one time, not two times. We did this for 50,000 times. Now, this amounted to running the robot for 16 hours a day for 700 robot hours. And so we collected the first large-scale data set in robotics for any kind of action, essentially. And what we wanted to show is that large-scale learning is really possible in robotics as well, especially in the case of self-supervised learning. And so we tried to show that performance really improves as you add on more and more data in robotics. And so I'm not going to go into the details of how we measured it. But what we were able to show was that performance improves with the increasing data points. We also tried to evaluate on things like clutter cleaning and so on. Once we did it with this grasping, we thought, okay, this approach should work everywhere. So then we went to drone. Can we navigate drones with lots and lots of data? Again, we need lots and lots of data. Can drones scale up at that point? So what we did was we made a drone whose only goal is to go and crash into objects. So this drone has skin sensor around it, and it goes and crashes into 12,000 different objects. So it's a crashing drone, essentially. What it is trying to do is it's trying to collect data of what it should not do. It's a negative example data collection. So it has to learn to not collide into these set of objects, essentially. The way we basically use these 12,000 scenes is we use the first part of the trajectory as positive, middle as gray area, and just before the collision as the negative data points. And then we train our standard deep learning pipeline where given an image, you try to predict whether it's safe to go forward or not. If you want to decide whether you want to move left or not, you can pick up the left part of the image and the right part of the image and try to decide whether it's safe to go left or whether it's safe to go right as well. And with this simple approach, we were able to really show really good drone navigation, especially in indoor. Now in indoor, drone navigation is really, really hard. Yet our model seems to work really good for these things. So you can see it's a Wien hall in CMU. I don't know if you have been to CMU ever, but it decides that this is a glass door, so it will basically turn again and goes there. So we can even do it in a narrow hallway with chairs as obstacles. So it decides that there's a chair. It has collided with chairs in the past. It says, okay, not I should try to turn left and so on. And so it can continue to, so here it collided once, for example, because it's a very narrow thing. It has to somehow control, and we are using very simple controls here, semantic controls here, essentially. And so again, you can see that it seems to work reasonably well with lots and lots of data. We can even have humans here. So for example, the drone tries to avoid the human while the human is walking, just because it has seen humans in the training data. There were students with which the drone might have collided in the training, and so it knows how to avoid humans as well, essentially. So all in all, the moral of the story is lots of data, but real world seems to work really, really good here. And so this inspired us to say, okay, if robotics can scale, can the visual representation be learned with these actions? So what we are trying to do is we are going to collect a large scale data of grasping, pushing, poking. Then we are going to learn a network where given an image, you try to predict some grasping parameters, pushing parameters, or poking parameters. Now, if you think the input is an image, so we can use all this network and say, this is our network which we want to learn. It's a visual representation. The only difference is that it has been learned for solving physical tasks like grasping and pushing. So what we wanted to explore was, if you take this network and fine-tune it for image classification or image retrieval, how good this network would do. This network has never done these things like image retrieval, it was only using this network for actions. And it turns out that it works really, really good, especially for image retrieval kind of problems. Even for image classification, it works reasonably well, but only on household objects, just because our data set was manipulable objects. And that's why it can never really scale on cats. Like cat detection would be really, really bad with this network. And so that brings us to this question, that even if we do robotics, so first, my summary observations with this experiment was that physical tasks are useful in visual learning because it tends to do really good on manipulable objects. And then multiple tasks help a lot. But there's still a long, long way to go. And that's what I want to focus on next, like where in robotics, how can we make robotics really scale for our visual task and other things? And I think the biggest problem in robotics is what has been the problem with everything, diversity. So how does currently robotics work? And I'm sure you have been reading all the DeepMind papers, Berkeley papers, and so on. This is what a DeepMind or Berkeley or OpenAI paper would look like. Either, and even our paper, by the way, from CAU. Either it will be in the lab, in lab, what you will have is a nice green tablecloth. Or in our lab, we use a white tablecloth. So it's a white tablecloth. Or you will have simulation. Lots of people are doing simulation. Why do they do simulation? Large-scale learning becomes so easy in simulation. I think in both these cases, the problem is diversity of environments. You're collecting data only in one environment, that is your own lab. You're probably not going to learn a lot. What made computer vision work? The diversity of examples in ImageNet. Similarly, in simulation, you're always going to learn some peculiarity of that simulator. And that is going to be basically some nuisance of that simulator. So what we need to do in robotics is not stay in these environments, but we need to take robots into homes. Of course, the first question that everyone asked when I presented this, are we even ready to take these homes? This is the same pattern of questions. When we said, okay, let's do robotics with large-scale data, everyone said, oh, robotics is brittle, you cannot collect millions of examples or thousands of examples and so on. So the same question exists here. Can we collect data in homes with robots? And the big problem is robots are too expensive and too brittle. I'm sure you have tried to ask your advisor to buy a robot and say, oh, $40,000. I'm not going to spend $40,000 for you, essentially. Or you would say, I'm not going to allow you to take the robot. It's a safety problem because at home and so on. So to tackle both of these problems, we are trying to do something. So for example, we have built this low-cost arm. This low-cost arm, it's a mobile manipulator. This costs less than $3,000. It includes the arm, it includes the base, it includes the computing power, and the depth camera and everything. And so this is a really, really cheap arm. $3,000 is less than now a cost of a good GPU. Not the Titans, but sure. So hopefully, once the cost of the robots come down so dramatically, we are hoping that now you can have not one, not two, but tens of thousands of robots going into homes and so on. But there's still a second problem, the brittleness problem. Robots are still too brittle. Cannot take robots into homes. Well, here I have a classical chicken and egg problem, right? I believe robots will improve when you have home data. But you will have home data when robots have improved. So I think this is hard to break. So how do we break this kind of chicken and egg? So our solution is, let's take it to real homes, but let's not have like real home users. And so we are basically going to Airbnbs. So what we are doing is we are starting to rent homes in Pittsburgh with Airbnb. This is now Airbnb rental. The robot goes, rents home basically, and starts collecting data inside that Airbnb home essentially. And so the idea is, if it is safe, it's still us. And so at the first try, what we tried to do was something very, very simple. We took our robot into Airbnb and we tried to collect the grasping data at large scale essentially. Now there's one big problem that happens when you make robots cheap. They become noisy. So if you're buying a Sawyer, which costs $30,000, and you tell it to go to location X, Y, it will go to X, Y. The error will be less than a millimeter. Now if you take my robot and take it, let's say, go to X, Y, it will go to X, Y, but the error is going to be 1 centimeter. Now, 1 millimeter and 1 centimeter, like in grasping, 1 centimeter is huge, and it's going to really kill the grasping problem. So, but this brings us to this new world of weakly or noisily labeled robotics data. Remember, we had such nice talks in the morning where we are doing noisily labeled image data. But now there's a new field that is going to come up, which is noisily labeled robot data. And so this is what we do. We try to take the robot, we try to have a noise modeling network, which models that if I'm telling the robot to go to X, Y, what is it likely to land here? How much is the likelihood that it is going to land here? How much is the likelihood it is going to land here, and so on. And for each of these locations, you're going to figure out, if I land here, what is the probability of grasping success? If I land here, what is the probability of grasping success, and so on. And at the end, you marginalize the two, essentially. And so with this simple approach and lots of data, so we collected more than 30,000 examples in 9 different homes. Here is the result that we get. And I think this is the most exciting result for me. And so the first result is very obvious. Again, all we are saying is, if you train in home and you test in home, you are going to do really, really good. But that was obvious, right? If you train on Pascal, test on Pascal, that's good. So and our approach does 62. If you take a robot trained with a lab data, it will only do 18%. If you train a simulation, a lot of people still claim grasping, for example, can be solved by simulation. The simulator does not work at all, and it solves only 28% if you're testing it in home. But I think this is obvious. For machine learning people, this is obvious. Now the next one is the most exciting one. What we are showing is that if you train on home data and go and test in lab, then also our model is much better than the lab data. So it's really learning, it's not only learning about the home data, it's actually transferring even to lab data much better than lab data itself. And finally, if you train on our model, using our data, which is collected on this $3,000 robot, and test the same model on a Baxter robot, which is $30,000 robot, again it works really, really good. So not only it's transferring across environments, it's even transferring better across hardware. And that I think is super exciting, because that tells us that for the first time we are really not learning nuisances of the grasping or nuisances of the environments, and probably learning something much bigger there. So this is the first problem. I still have time, right? 5 minutes? Yeah. So this is the first problem of diversity, the environments. But diversity comes in different ways. The second problem of diversity is tasks. Remember, most of the people who create robotics dataset, like I created the first one as called grasping dataset for robotics. Then Berkeley people created pushing dataset for robotics. Then there was someone who said, I'm going to create poking dataset for robotics. This is like 2000 in computer vision, right? Someone was creating phase dataset. Someone was creating car dataset, and so on. But none of this helped us solve computer vision. What made computer vision work was when things like Pascal or ImageNet, like lots of categories came together. Why did it work? Because now you can transfer across categories. You're learning representations that are going to not work on one category, but multiple categories essentially. And this remains a big problem in robotics. You really have this lack of data sets which will do lots of tasks. And when in robotics, whenever you'll hear of task, a lot of time you'll hear that one task is picking up a red block, other task is picking up a green block. Those are two different tasks. But that is not task for me. Task is like the way we define task in computer vision. And so what we are trying to do is we have collected a large-scale demonstration data set, which is basically we have humans that do a task, for example, opening bottles. We have robots, then the humans make the robots do the same task by collecting kinesthetic trajectories. And then we also have the egocentric data for the same task and so on. And so we did this for 10,000 different kinesthetic trajectories. It took us 8 months to collect this data set of 10,000 different trajectories of 200 different tasks with different objects like typing, soft toy, raising or opening bottles, wiping with this and so on. And so this is going to, we are going to release this soon. This is a paper that got accepted yesterday. And so hopefully you guys can also use this large scale data set. We have lots of experiments where we try to show that you can use this data set to do imitation learning and so on. I'm not going to go there. But the whole idea is that we need to start creating data sets which will do diverse tasks. The third problem in diversity is diversity of hardware. And this is something which exists in robotics. And robotics people think this is the curse that they have. Like every lab has a different hardware. So every time we want diversity, there is one diversity that exists, but that is presumed to be like problematic. That is because you cannot train one model that will work across all the hardwares. If you have collected data set with Baxter, you can only train Baxter. This model will only work on Baxter. If you have collected data set with Sawyer, it will only work on Sawyer and so on. The biggest problem, why is this happening, is because when we are trying to model the problems, like learn policies, we will learn policies that are invariant to hardware. That is what domain randomization and stuff. Like you will train it with different dynamics, and you say, I want to learn policy that will work on all the dynamics. That is something what we do in computer vision. That's the argument, right? Illumination. The same model should work for different illuminations. But in actions, that is completely wrong to do. You should not learn policies that are invariant to hardware. You should learn policies that are variant to hardware. So until now, you learn policies that take state as input. From now on, we are going to take policies that take state and the hardware qualities as input. So for different hardware, there will be different action that will be taken. If it's a 5 degree of freedom robot, it will be a different action. If it's a 6 degree of freedom robot, it will be a completely different action that we are going to generate and so on. So the action policy is going to be a function of both state and hardware. And so what we did was, so this is an experiment we did in simulation. We collected data from 10,000 different robots with different degrees of freedom, different dynamics, different kinematic lengths, and so on. And we tested on something completely unseen robot before. And I basically somehow missed the slide. But what we show is that the performance is much, like this transfers really, really well to the hardware that we have never seen before. Okay, with that, I think I would like to conclude that I think the clear thing that we need to do is move out of the supervised learning and go into the learning where you can have self-supervised or unsupervised learning. You need to be interactive in nature, no more passive learning. This is something which is so artificial if you think. And finally, I believe we need to have physical data physicality is going to be crucial to learn vision and common sense. And I think only way we can do it is if we take real robots in real homes, because that's where the real common sense lives, not in your lab and something like that. And so I think with that, I will end the talk.
All right, thanks for the speaker. Is there any questions? So let me remind you that you can put your questions online with Twitter by using the hashtag BMVC2018, and then we'll be able to read your question here. Alternatively, we have a few microphones there as well, so you can just raise your arms and ask questions. So for that.
Professor Gupta, thank you for your talk. So I wanted to know, like in some tasks, the diversity is a curse. For example, if we are looking at images that are not natural and we want to learn those. So what are your thoughts on those kinds of tasks? Thank you.
So if you're trying to learn for a very specific task, I think in that case diversity is not natural, because that's what if you're sure that in the test data you're never going to see this images like from this distribution, why do it in the learning? I think I agree with there that if you're never going to see an image that is guaranteed to occur in the test, there's no point getting that kind of diversity in the training data. But by doing this talk, I'm trying to learn this generic representation that is going to work everywhere. And I think in home or in real life, we can never guarantee what's going to happen and what's not going to happen. So you really need to get as diverse as possible, just so that you can be ready for all kind of training situations, or you have seen as many situations as possible inside training data itself.
Okay, so in your case, the diversity actually helps the model to learn better representation. So I wanted to know, like in cases where the diversities cannot be used, what can be used to learn similar kind of representations, like auxiliary diversity kinds of representations?
I mean, I think generally in those cases, what you try to, if you are looking at a very specific task and very specific domains, you make sure that, to make sure that you're not overfitting to your training data essentially, what you try to do is you try to put regularization, some kind of regularization and so on. I think the biggest problem is you have to design those regularizations by hand, like in machine learning, like you want weights to be small and all those kind of things. They might or might not make sense. I mean, mathematically they make sense. It's optimizable and all those goodness exist of the world. But it might not be the right thing because your model might be learning something completely different kind of a nuisance factor and so on. So, frankly, the answer is I don't know the answer. But regularization of some kind, I feel diversity has always helped us just because our testing conditions are very vague. And so the more diverse you go, at least you are making sure that the task, you're not learning something very specific to the input. You're learning specific to the task, not to the input. So that's why diversity seems to have helped us a lot in the training.
Thank you so much.
Any more questions?
There are lots.
Yeah.
Hi, thanks for the talk. We already have a couple of examples of robots in homes. I mean, the Roomba is perhaps a big example. And we also have robots in factories also, of course. So in the case of the Roomba, localization is perhaps the main task it could do. In factories, there are for manufacturing. So are there good examples of tasks like that we could try to be employing these techniques?
So I think you're right. I mean, I should have clarified it that this is the first attempt for manipulable robots to be inside homes, not just any robot. I mean, you can even consider Alexa and all those things as robots as well in a broader definition, whatever you want to say. So when I'm saying manipulable, that's what our hope is, that there's a couple of tasks where we are going to make them like Roomba, really, really good at, so that we can stay in the home of people, right? I mean, that's what we would want to do. We want to stay in the home, not just have catch their fantasy for 1 week and then just because it does nothing, lose it. But again, I think this is a very hard thing. I think what I will say is that we are just taking the first baby steps of homes, essentially. There is a big line of multiple years of research here that has to happen before any of that can happen. But I am open. If someone has a really good idea of a task, they think that is, for at least to them, it's solvable. I would love to get that task so that I can take it out to the people really.
Hi, thanks for your diverse talk. I have two questions. The first is in your first part of your talk, the tracking of the patches. What kind of data do you use to be able to track your objects through the scene?
So, this is actually because I was running through these things. So first we downloaded data from YouTube, like 20,000 videos for that. Second, we made sure that the tracking algorithm is not learned. So it's a non-learned tracking algorithm essentially, because if it is learned, then it defeats the purpose essentially. So I think the tracking algorithm name is SDS. I don't even know which one is it, but some kind of tracking algorithm which is not learned essentially. I think it's based on Lucas Canade kind of features essentially, something like that. And so that's what we used. And the videos we downloaded with, so there's a standard data set in one of the papers for videos. We just took that data set and we started. I do have to say that the videos are biased, that those videos are very likely to be having ImageNet kind of style. It's not random videos. Because if you start downloading random videos, you will mostly see dialogues like news and stuff like that. So it is a little biased data set of videos that have been downloaded, but we didn't download it, someone else downloaded it. So that's our only thing to say we are not guilty, essentially, of some biases that have cropped into the data set somehow.
Thank you. The second question about the self-supervised learning. You might know that people sometimes don't want to learn things, but it's good for them to learn. How would you have this paradigm in your self-learning? Maybe your robot thinks, I don't want to learn red objects.
Right. I think, so this is something which is with lifelong learning. So this whole notion of introspection and stuff like that comes into play, like self-evaluation and so on. So the only reason people will say, I don't want to learn about rats, is because rats are not going to hurt them or harm them or so in any way. So why do I care about it, right? So this is like a risk minimization. It's much more energy spent in learning rats than anything usefulness coming out of it and so on. These are much harder questions, longer term questions, I would say, of deciding self-evaluation and deciding your own risk and energy constraints and so on. None, for us, model is trying to just learn to maximize performance on a test data set. That's what the model is. If there's a rat in the test data set, it should go and try to learn rats, essentially, is basically what we are. And since it's impossible to say what is going to be in test data set, the model wants to learn everything it can learn.
Thank you.
Yeah.
This is regarding the first part, regarding self-supervision. So you were treating the ImageNet model as the benchmark. So in the long term, do you think that do you want the self-supervision to cross the ImageNet, or will it always be lower than the ImageNet?
So I think there are two interesting questions here. First, what you're saying is that, and I think it's a very valid question, that while you're doing all this research in self-supervised or unsupervised learning, Vito is collecting more data, right? I mean, so I should be comparing to whatever Vito has today, not ImageNet, which was some time ago or something like that. That is true. The only problem is we are not even able to beat ImageNet yet. So Vito is farther ahead in the line of baseline models, essentially. Now, the second question, what you're asking is, do I think that we are going to ever cross ImageNet?
Yeah.
If we don't, I think it's a very sad story. But I think, personally, I would want it to cross ImageNet as much as possible. This is something which can never be granted. Like, I mean, the question you're asking is unsupervised learning going to beat supervised learning? I think a lot of people hope that. It's just that it's not yet there. I mean, we cannot guarantee when will it, but that's what it is right now. I mean, but this is good, right? I mean, more papers to publish, as that's what everyone says, that keep publishing until you have crossed that line, essentially. Yeah.
Thank you.
So we've also got a few questions from the online feeds. So the first one is quite interesting. More data is bad news for small labs at university due to the limited resource. So unlike big resourceful companies, shouldn't we shift the focus to improving the learning algorithms?
I think, so it's a very tricky question, by the way, I have to say. So it is what it is. I mean, it is basically that it does seem that big data or more data is always useful in the long run. But that doesn't say that the model performances have also saturated, essentially. So I actually removed one slide. So there was another slide which I had in my large-scale learning talk, which showed that you can also get more performance improvements if you are actually changing your models. Like a ResNet 152 seems to work better than ResNet 101 on the same amount of data with 300 million. And as the more data set size increases, the gap seems to be bigger and bigger, essentially. So what that tells me is that there is a lot more research to do in the space of models as well. I think, definitely there are people who have more computation has little benefit, like little more benefit there. But I think I would say that there's still a long way to go even in the model and representation. Like, for example, for videos, for example, I think we just don't know what is the problem we are trying to solve. That's where I think academia has a long role to play, or people, we still have a very, very long role to play and so on. So there is I would not think that there is only one problem or something.
So another question is that apart from asking the robots to simply touching things or seeing things, have you ever tried or have you considered to ask the robots to consider other type of interactions, such as smelling?
Such as?
Smelling.
Oh, that's again a very good question. I think smelling is too far. I have no idea how smelling works. The best we have gone up to is haptics. So I didn't talk about my haptics work at all. So we have been trying to do a lot of haptics as well, especially trying to develop haptic sensors which are soft skin. So we are trying to put skin on the hands of the robots, just because by touching things you can do a lot of learning about the world. So that is one area where I think you should see a lot more happening in the next near future, because haptics is something where things are starting to work reasonably well. I am starting to see a lot more papers. Smelling, I have no idea what is the state of the art in the hardware of smelling yet. I'm sure there is someone doing research. I think it's all dependent on the hardware. So robotics, unlike, even computer vision was dependent on GPU hardware. And so when GPUs came, then that's when the computational power came. I think in robotics, it's even more, like you need to have the right hardware, only then you can start to move into these areas, which are this.
So allow me to pick one more question from the feed. Say this one. So in the grasping demos, did you simply learn the grasping motion, or did you learn some complex control parameters?
Oh, that's a very good question. So we didn't learn any. I think it will be wrong to say that we learned any complex parameters, because the way we are defining grasping, if you look at here, is we are defining what location should we pick and what angle should we grasp at. And then it's done by a standard lower level. So there's a lower level module which basically does all the conversion from this higher level semantic space into the torque space or action space and so on. We didn't do any of this here. However, that said, the later part of the approaches here is basically doing everything in torque space essentially. So I think it's a mix. Sometimes we are doing it in torque space, sometimes we are only doing it in semantic space. We are not trying to do a lot of this in,
Okay. There's still more questions online, but I'm afraid we don't have enough time to go through all of them. So I would suggest you to bring your questions, and later on during the receptions, you can continue to discuss with the speaker. So let's thank our speaker one last time. Thank you very much.
I need this one.
So I'll just introduce you by yourself, your machine. Yeah. Okay, so let's continue to the next speaker. Zeynep will be our next speaker. Zeynep Akata. She is an assistant professor with the University of Amsterdam in the Netherlands, a scientific manager in the Delta Lab, and also a senior researcher at the Max Planck Institute of Informatics in Germany. So her research interests include machine learning combined with vision and language for the task of explainable artificial intelligence. And she has a very sharp publication track record in CVPR and PAMI. She also is the recipient of this Nancy Manner Award for Excellent Women in Computer Science. So today she will talk a bit more about explaining and representing novel concepts with minimal supervision with us. So can we give some support to our speaker?
Thank you. Before I start, I would like to thank the organizers for inviting me and also for this nice introduction. I'm also going to talk about how we do classification recognition using minimal supervision, but from a slightly orthogonal point of view. I use language a lot in my research, and I will give an overview of my research in the past couple of years. First, I will start by motivating the importance of side information being language in my case. And then I will talk about generalized zero-shot learning, which is the extreme case of having lack of visual training data. How do we do classification when we don't have any example images? And my very recent research interest is explainable AI, so I will introduce my understanding of the topic, and then I will summarize and talk about some future works. Let's start with motivating the importance of side information. So when we look at large-scale data sets, like ImageNet, we see that the data distribution has a very long tail. So we have a lot of examples of cars, objects that we often see around us, and those objects are also very easy to label. But there are some objects that are very rarely found in the nature, and also if we are not trained to name them, we don't know the names of those objects. So it's very difficult to get enough labeled data for those concepts. But when we look at ImageNet, we have more of these classes than these. So I focus on classification in this portion of the data set. When we don't have labels, we can infer labels using some intermediate representations like attributes. Attributes are visually discriminative properties of objects, like black and white, has tail, lives on land, small. I think of attributes as class-level concepts. So some of these attributes are common for both of the classes, those examples shown here. So the vector that we are building using those attributes will have the same value. And then some of these attributes are specific to one of the classes. So this vector will have the value 1, and this will have the value 0. And then some of these attributes are relative to each other. So we can also have values between 0 and 1 in this case. So zero-shot learning is, like I said, the extreme case of having lack of labeled training data, which means we have enough labeled samples from some of the classes. We have access to their attributes, and for some of the classes we don't have any labeled images, but we still have access to their attributes. This is how we can associate between different classes. So the next step is the model, which is also very important. I'm using multimodal embeddings framework, which is composed of 3 different steps. So we have images that we embed in an image feature space, which can be built using low-level features like Swift or Fisher vectors like we used to do before, but now deep learning replaced it. So we have a pre-trained network trained on ImageNet that we use to learn these feature representations. So these are given. And then we have labels that we embed into the class attribute space, the way that I showed before. The next step is to find the compatibility between these 2 spaces. So we are given these theta vectors, the phi vectors, the xi related vectors, and we are trying to find the parameters w. So the loss function can have many different flavors. We are minimizing this empirical risk using a weighted pairwise ranking loss. So the loss function looks like this, which essentially says for the image, the sample, the selected sample, if the predicted label is correct, then these will cancel out. and this will be 0. So there is nothing to do. If the predicted label is incorrect, we will have a positive loss that we are trying to minimize. And this compatibility function, in my case, has this very simple bilinear form. Like I said, x's are given and cy's are given. Those are the vectors. And then the w's are the parameters that we are learning. So there are two different zero-shot learning tasks. One of them is we are learning classifiers to generalize to unseen classes. So in our search space in the end, we will have only, we will search among the labels that we have not seen before. This is a restrictive setup, so people have come up with generalized zero-shot learning, which generalizes to both seen and unseen classes. So when you have unlabeled data, you are projecting it into that attribute space, and you are searching for the closest attribute vectors among both seen and unseen classes. So I'm going to show some examples, but first I want to talk about these two fundamental data sets that we use for zero-shot learning. Animals with attributes has 50 classes and 85 attributes. Images, some of the sample images look like this. We use 40 classes for training and 10 for test. And Caltech birds dataset is a fine-grained bird dataset that contains 200 classes of different kinds of North American birds. Because the objects look very similar to each other, we need many more attributes. So we have 312 attributes. So one issue with zero-shot learning is, these are the average per class accuracies on birds dataset, on animals with attribute dataset in the zero-shot learning setting, when we have only unseen class labels to search from. And this is generalized zero-shot learning. We compute accuracy on unseen classes and seen classes separately, and then we take their harmonic mean. And when you look at the results, you see that the results decrease significantly, which also shows the difficulty of the problem. But this is not the only issue. So multimodal embeddings framework works well. These are, believe it or not, state-of-the-art results. But simple softmax classifiers don't work in any of these cases because you need to have samples to train with. You need to understand the meaning of the label first. So as a conclusion, I wanted to convey that first, standard image classification models fail when we have lack of labels. And then zero-shot learning is a challenging task that deserves attention, and we need side information to be able to solve it. There is no other way, but there are many different sources of side information that we can use or build representations from. So this motivated me to move towards free text. Now I want to talk about generalized zero-shot learning with side information. So because the labels are difficult to obtain and attributes require expert knowledge, especially in case of fine-grained data sets, we proposed to solve this task by generating images from scratch using sentences, using free-form text. For that, we had to first collect sentences for the fine-grained data sets. So for the given Caltech birds dataset and another Oxford flowers dataset, we asked annotators in Amazon Mechanical Turk who don't know anything about these objects, they didn't need to talk about the discriminative properties of these objects, whatever they thought is discriminative, and not talk about the background or the action. And they came up with these very detailed one-sentence descriptions of these objects. And then for every image, we collected 10 sentences, which costs less than collecting attributes for these images. The next step is to build vectorial representations like we did for attributes. For that, we use convolutional recurrent neural network in which we treat every character as a vector. It's a binary one-hot vector. Depending on the position of the letter in the alphabet, that position of the vector will have the value 1, the rest will be 0. And from that point of view, a sentence is a matrix of zeros and ones on which we can do convolutions. After we have some convolutional layers, we also stack the recurrent neural network on top of it to model the history, to include the historical information in the generated or predicted representation. So in the end, we have a vector that represents this sentence, but we need per class vectors. For that, we just took all the vectors that belong to the same class, or all the sentences that belong to the same class, and we simply averaged them. So the next step is now we have sentences and we have vectors that represent them, but we still don't have the images that reflect the content of these sentences. For that, we used generative adversarial networks that are conditioned on the textual representations, per class representations, although I show here sentences annotated on an image basis. This can be actually anything. It can be also attributes. So the GAN framework, as you probably all know, is two networks that are competing with each other, that are playing a zero-sum min-max game. The generator is trying to generate as realistic images as possible, and the discriminator is trying to detect whether these images are real or fake. So normal GANs start with a noise, and then there is upsampling, and then in the discriminator it's a very simple convolutional network that says that outputs the labels 0 or 1. In our case, we have also it's a conditional GAN, so we attach or concatenate the sentence representation to the noise and then normal upsampling. And in the discriminator, now it needs to say real or fake, also based on whether this image and this sentence matches or not. Some results. So we see that the images, the content of the images follow the semantic content of the sentence. For example, dark red, it talks about a dark red bird here, and all the images show birds of color red and white and blue. But of course, when we look closely, the images or the objects are missing body parts. This was the first attempt, and then this network has been improved over the last couple of years. One flexibility that the sentences help with or enable is we can actually take a sentence and generate an image that looks like this: bluebird with black beak, and redbird with black beak generates this image, and then we can interpolate between these sentences. And then, although the interpolation between this embedding and this embedding may not actually mean anything, we see that the interpolated images make sense. So this can be used as a data augmentation mechanism. So what happens when we do that for zero-shot learning? So when we have only real images, and we learn classifiers using like multimodal embeddings, using only real images, we have this accuracy. And then when we use generated images, when we generate images and extract features from them and add those features to our training set, then we get this result, which is not better than having no images. This is slightly discouraging, but there is a solution to this. We thought if we are trying to improve zero-shot learning accuracy or classification performance, then we actually need image features. We don't need images per se. So instead of generating images first and then extracting features from them, which leads to noisy representations, maybe because the images don't look realistic, maybe because of the blur that they have, the CNNs don't work, the effect adversarial images also lead to. So we decided to generate image features directly using a very similar GAN framework using sentences. So again, going back to the previous table, we had these results using generated images, and with generated features, we improve results significantly. So this essentially solves the problem, well, up to some extent. There is still lots of room for improvement, of course. As a conclusion, I wanted to convey, again, language complements visual information because it provides an intuitive interface for the model. We also see that language representations are strong and generalizable. We have used them for image classification and generation, but they also open up potential for many other different applications, which brings me to the last part of my talk. How do we do explanations? How do we generate explanations and try to build deep models that are interpretable? Okay. So first of all, according to my notation or my terminology, there are two different explanations. One of them is introspective explanations, which are trying to come up with a deep model that explains itself. For example, if filter 5 is activated, then the result is going to be like this. It's more tailored towards the developer, so to say. There is also the second type of explanation is introspective explanations, rationalizations, which is post hoc explanations. There is a deep model that is a black box. We don't have access to how it thinks. But another deep model is trying to explain the first model's decision. So in this scenario, we have a user. So we have the user and the machine, and they are communicating with each other through language. The user can ask any type of question that they want. In this case, we have this application, fine-grained classification. And the user asks what type of bird is this, and the machine says it's a cardinal, and this is how image classification models gives us answers, which is restrictive. We don't understand. If we don't know what is a cardinal, we don't know if it is a correct decision or not. So one way of improving this answer is to extend it to a sentence, but a sentence that doesn't talk about non-cardinal specific properties, but only cardinal specific properties that are also visible in the image. So our answer should look like it's a cardinal because it's a red bird with a red beak and a black face, which are very visually distinguishing properties of this object. We have so we built a visual explanation model, language-based explanation model, a post hoc explanation model that takes an image, and then there is a black box model that gives us an image feature and a class label. And then a language model, it's an LSTM, is conditioned on the image feature and the class label. And it is trained using linear combination of two losses. One of them is trying to predict the following words given the context, the usual LSTM. Another one is trying to make the sentence more class-specific. So after generating a word, we evaluate the sentence. If the sentence with this new word has enough information to be classified correctly, we have a high reward. Otherwise, we reject the word and sample a new one. So generated sentences look like this. And then some examples. So first, for the image, a label needs to be predicted. We have a template. It always starts with this is the class label, because, and the rest of the sentence is generated by the LSTM. This is a black capped vireo because it talks about the black head, which is important property. And then crested auklet because it has white eyes, and then green jay because blue head and a black throat. So the difference between descriptions and explanations is descriptions can talk about any property, but the explanations need to talk about class-specific properties. So one challenge that comes from the data set is, so these two images belong to the same class, downy woodpecker. The predicted label is correct in both cases. When we look at the descriptions for these two images, so this one is a male bird. It has a red spot on the neck, and this is female of the same species. It doesn't have that property. So the description model talks about the red spot, even if it is not present in the image. The explanation model doesn't. So this is one improvement. But not in all cases it works very well. So some failure cases, again because of the dataset issues, this image and this image belongs to the same class, Lysan albatros, but this is a juvenile bird. So when it grows up, it will look like this. The predicted label is incorrect, cactus wren, and the explanation follows the properties of the cactus wren, because those are the visible properties in this image. It's not able to detect the shape of the bill, for example, which is very important for this class. So coming back to the motivation, so I talked about generating explanations in this way, but this model is still quite weak because we don't know, we don't have any evidence of whether these properties are actually visible in the image. There is no mechanism to penalize it and not mention those properties if they are not present. So one way of improving it is to detect boxes around body parts that are mentioned in the sentence and reject the sentences if these properties are not groundable in the image. And then also this allows arguing about a counterfactual class, a class label that should not have been predicted for this image. So in this case, the user might ask, why not a vermilion flycatcher? And the network needs to think about an example of that species and then figure out what are the distinguishing properties that is visible in this image, but not in this image. In this case, it's black wings. So we generate sentences that look like this. It's not a vermilion flycatcher because it doesn't have black wings. And we call them counterfactuals. So the base model is the same. We start with this, the same explanation sampler. We take this image, the generated image, and then we divide this, generated sentence. We divide it into multiple noun phrases. In this case, red beak, red bird, and the black face. And we have an explanation grounder. It's a grounding model that is trained on a completely different task, visual genome in this case, because this data set doesn't have bounding boxes. So it is able to recognize what is a beak, for example. And then the next step is we sample multiple sentences like this. We generate multiple sentences, and then we try to ground every noun phrase in this image. And then we rank the sentences based on the cumulative score of every noun phrase bounding box match. So in this case, the red beak is the correct, there is a correct match, so the score of this union is going to be higher than this one. So the score of this sentence will be higher. So this is the sentence that we accept. Some visual examples. So this way of grounding explanations is helpful not only because we generate sentences that are more class-specific and image image relevant, but also we have bounding boxes that also act as visual explanations. So it talks about the red spot on its wing wires. This is the grounding visual explanations model, and this is the baseline generating visual explanations model. Yeah. And then for the counterfactual explanations, so the model sees these images, and this I provided as an example of the counterfactual class. So the way this sentence is generated is first we generate a positive sentence for this image. So it's a crested auklet, the predicted class, because of these properties. And then it's not a red-faced cormorant, it's the visually the closest class to this image. And the properties that are often mentioned for this class contains this long flat bill. So, and these properties are not groundable in this image. So we choose the counterfactual phrases based on the class-specific phrases for this class that are not groundable in this image. I also wanted to show the difficulty of the data set. So these two images belong to a completely different superclass. So auklets versus grebes look very similar to each other. And the only distinguishing property is the eyes, and the counterfactual phrases talk about them. Okay. So one natural question that comes to mind is, so I talked about birds, but this is not really applicable to our daily lives. And also, I talked about labeling images or generating sentences or describing images, which is also restrictive. So we also attempted to explain videos and self-driving vehicles in this application. So we have a data set that contains 30 to 40 second long videos that are taken from a dash cam that is mounted in the mirror of the car, and so the driver is driving. And then we also collected explanations of what is happening in the scene from the point of view of another person. So somebody, and the annotator watches the video and says the car is turning right because of this visual evidence. For example, there is a turn right sign. Coming back to the motivation, we want to annotate, or we want to generate explanations for this kind of scenarios. We have videos, and the simplest explanation, well, the description would be the car is moving forward in this case, which is a prediction. Now, the next natural question would be, why do you think so? And the next natural answer should be, because there are no cars in its lane in this specific case, with an attention map that is overlaid in the image that shows the visual evidence of this prediction. So our driving explanations model takes a video, and there's a convolutional network that produces a special attention that we overlay in the video. And it also predicts the course and the acceleration of the vehicle. And those are going to be the conditioning variables to the language model. And the language model can have, so we evaluated two different language models. First one has only temporal attention, and it gives sentences like this: the car is moving forward because there are no cars in its lane. or the language model can have its own special attention that will produce an attention map that we can compare, basically. And then this model generates another type of explanation. It is difficult to say one is better than the other. Also, if you look at the results, it's not really one is better than the other, but just to have these two different models, we have shown results. So basically, the videos look like this. This is the real video. And then these attention maps are generated by the vehicle controller. So the vehicle controller looks at these regions. And then these attention maps are generated by the explanation generator. So the explanation is generated, so this explanation is generated using this attention map. It says the car heads down the road because the traffic is moving at a steady pace. We included a lot of examples in the paper, so feel free to take a look at them. There are failure cases, of course, but most of the times we were satisfied with the results. As a conclusion, generating visual and textual explanations is a means for model interpretation, which is necessary to improve deep models. And also they are very important from the user's point of view to trust the deep models. And it's a step towards an effective human-machine communication. If we are going to employ these machines which take decisions for us, then they better communicate with us the way we communicate with each other. Okay. So as a summary, I talked about multimodal joint embeddings and how we tackle the lack of visual data problem. I talked about the importance of side information. I tried to argue that vision and language complement each other for generating novel concepts. First, I talked about attributes, and then we moved to free-form text, and we could generate images and then extract features from them as a data augmentation mechanism, or generate features directly. I also tried to argue that developing explainable deep models is important for user acceptance. And you can read more about these from these papers that I cite here. But the ultimate goal, basically from my point of view, how the future of explainable AI would look like, is a model which can argue what is happening in a video in a completely natural way, which is not any different from the way we communicate with each other. So when we look at, for example, this video, we see that there is an activity that is happening that needs the driver's attention. So until a self-driving car generates explanations or dialogues that look like this, I think we have a very long way to go. So basically, in this dialogue, the self-driving car is explaining what decision it is taking and why it is doing that. For example, I'm driving down an empty road, which corresponds to this frame, and then suddenly a ball appears on the right, which is the most important action that happens here. And then I'm slowing down because now the ball is in the middle of the road and there is a child running towards the ball, so I need to stop. And so this might still be doable with the current models, but something like this is not possible because at the moment, what happens if you don't stop is a legitimate question. And answering this question requires contextual knowledge, like, for example, an argument of what would be the impact of this action, and then what would happen to the actors in the video. So there is still a lot of research to be done in this direction. This is all from me. Thank you for your attention.
Thank you very much for the presentation. Is there any questions from the audience? Again, you can trade online or you can just raise your arm. So, can we have a microphone for this gentleman over there?
Thank you for your talk. So you said that your interest about explainable AI. So my question is from that. So now the model is generating text which is being verified by another model to make it explainable. And then you gave at the end of your talk an example about how the future might look like, where it is generating sentences. But do you really think that in the future the self-driving car might be like communicating with the passenger or the humans at all? And if that's not the case, then do you think it is really relevant to generate this kind of sentences, or how language is relevant in explainable AI in the future? That's my question.
So from the user point of view, I can only talk about myself. If I'm driving a car, if I'm letting myself inside a car that drives me around, I would want it to communicate with me. So I would want it to tell me when it is taking an important decision and why is it taking it. So I'm thinking here from the user point of view, and I think it is really important for the not only for self-driving car scenario, but also to be able to understand when a model is not working well, why it is taking a wrong decision, and to improve it. Explanations also are important in that sense too.
Yes, but the explanation is also generated by another model, so that is also optimized for some loss function. So how can you be sure that that is the correct explanation which is being generated, or does that really make it explainable?
So post-hoc explanations are a little tricky. I always get this kind of comment when I give a talk about this. But let's assume that we don't have access to the internal thought process of the model. Somebody has shown the through, I don't know, maybe accuracies, that this model is working well, and they are going to implement it in a device that I'm using. I can say, okay, I cannot really explain the model that is taking the decision, but I think something that is better than this is to use a model that is explainable, that explains the first decision maker. And this is not much different from how we justify each other's behaviors too. So I cannot know what exactly you are thinking, but I can very easily say, when you do something, you probably did it because of this.
Thank you so much.
There's a question from behind. Can you pass him the mic?
Thanks. You encode your sentences using one-hot vectors of letters. I just wondered if you could tell us how that performs compared to encoding one-hot vectors of words.
So we tried it for zero-shot learning. Extracting representations and then using them as a side information for zero-shot learning. So when we use one-hot vectors for words, it performed worse than one-hot vectors for characters, quite significantly.
Hello, thanks for the talk. So a couple of talks we had were about generating huge data, very large scale data set. On the other hand, in the zero-shot learning, it's completely orthogonal, where we do not have any data. So how do you see this related to this? Because in the zero-shot, we already have the data and then we split it into the seen and unseen. So where do you see the practical applications of it? Because already we have ImageNet and many more data sets coming up. So will it be having some applications in self-driving cars or something else?
So zero-shot learning is quite academical setting still.
Yeah.
So I don't think there is much future in pure zero-shot learning because of what you have identified as a problem. But generalized zero-shot learning is, I think, more applicable to relevant problems, like relevant applications. Also, there are ways of, so I talked about inductive zero-shot learning approaches, but there's also transductive zero-shot learning. And this is another interesting area, which is for the people who don't know it. So you have a lot of unlabeled data that can come from unseen classes or seen classes. Typically, it's from unseen classes. And there are ways to use this unlabeled data that come from unseen classes to improve zero-shot learning performance. I think that's also another realistic scenario.
Yeah. Thank you.
Any more questions? Oh,
So I have a question in your zero-shot learning setup, the generalized zero-shot learning.
Mm-hmm.
You said that, so for the unseen classes, you projected to attributes which you have seen.
Yes.
So how much of performance that you're getting, the gain, is because of better projection? So you got a major gain, but that could be because your projection became stronger, that you're projecting to the right attributes, and the initial cases you were not projecting to the right attributes. Would that be one of the reasons why?
You mean, so the difference between multimodal embeddings and the softmax case?
No, this is generalized itself. So you had this CNN-based sentential representations,
Yeah.
etc.
Mm-hmm.
So in the first case, without sentential representations, you're getting a particular result.
Yeah.
And in the sentential representation case, you got a boost. In one of the cases, you got the boost. I was wondering, is that because of the projection being stronger? So you're projecting the unseen attribute to a very good seen attribute.
Oh, I see. So the training set is not any different. We always only have seen class, the images that come from seen classes. This is how we learn the embedding. In one case, at test time, your search space is restricted to unseen classes. So you project the image onto the attribute space and look for the closest attribute vector among the unseen classes. In the other case, you include all of the classes. So what we see is the reason for the drop in accuracy is because you have only explored the space around the seen class embeddings. You always project the images on close to the seen class attributes. And then you are always very far away from the unseen class attributes. Some people call it the domain shift problem. Yeah.
all right. So there are a few questions from the Twitter's account. So this is an interesting one. How to make a decision for the vehicle A in judging whether the car is moving forward or backwards?
Forward or backwards?
Yeah. So how can you tell whether the car is moving forward or backwards?
Okay, so you actually, the features come from the video, so we are not analyzing one single image. There is temporal dependency, but there is never, okay, maybe there are some backward going cars too, but probably this gets disentangled from the temporal dependency of the video frames.
I think so. And another question is like, do you think a language model is likely to introduce human bias into the model, unlike a visual one? So how can you guarantee that it will not influence the model negatively?
Yeah, this is a very good question. So the only way that we can train our models at the moment is by using human annotations, and they are biased to the way we think, and yeah, maybe that's a weakness.
Yes, that's true. This is probably the last one. For the free text-to-image synthesis using CGAN, how do you append the sentence to the noise? Do you need any specific modeling for the conversions?
No, it's just simple concatenation.
Oh, okay, that's good.
Yeah.
So I also have a question, which is like in your synthesis and also in your explanations part, I think a lot of these tests, they're based on textures or colors. So how difficult it is to include more about, say, for example, geometric features such as the shapes or maybe the size, that sort of things? Is it more of implementation challenge, or is there anything technical inside?
Yeah. So another aspect that I heard criticisms about. In the case of birds, when we generate images or when we do also generate sentences, most of the times birds are viewing right or left, and there is probably a bias in the data set that the models are exploiting at the moment. So I can't say anything about this, but so we didn't tune our models using this prior knowledge, at least. Yeah.
So yeah, I think that probably is it. Is there any more questions for the speaker? So let's thank our speaker one more time.
Thank you.
So I hope you enjoyed today's tutorial. Just a few reminders before we move on to the next part of the conference. So tomorrow, if you need to have a poster sessions there, then you can actually start sticking your poster in early morning. So the poster board will be available already. So you need to remember that there are 3 different poster areas. One of them is outside this room. The other one is upstairs. And the third one is downstairs. So you make sure you go to the right room, stick your poster in the right number. Otherwise, people will just tear it down. Also, if you have a spotlight session tomorrow, please make sure you arrive at least 15 minutes earlier than your sessions. And then Daniel will arrange with you on how you deal with the spotlight, just to make sure it's smooth. So the next part of the conference will be the reception. The reception will be something like 10 minutes walking distance from here. So you experience the UK weather. I think it's just heavily raining, and right now it's a bit better. So hopefully you don't forget your umbrella. And we'll have some student helper guiding you through. So just make sure you bring your reception drink ticket, which is the one marked with Monday. And there you can exchange it with whatever drink you want to have. So I'll see you in the reception like 15, 30 minutes later. Okay, see you soon.